Homework 12, Polynomial Division, Factor Theorem, Rational Zero Theorem, Video 5. As you can tell, as I'm erasing some remnants from the last video, that I preserved the division problem from the last video and its answer, no remainder. Now, why did I do that? Remember what's motivating all of this division in the first place. In the previous series of videos, we were attempting to find x-intercepts of polynomial functions by putting them equal to 0 and solving. If those polynomial functions were already factored, it made it a lot easier to solve. But if they're not factored, we have to get them factored. What does that have to do with this? Well, if you have a division problem whose remainder is 0, and I'm going to explicitly write that the remainder was 0 for this division problem, we can take advantage of that. How? Because any division problem, such as 24 divided by 4 equals 6 with no remainder, any division problem without a remainder can be rewritten as a multiplication problem, basically checking the answer. How would you check the answer of 24 divided by 4 equals 6? You would say 6 times 4 is equal to 24. Well, the same thing applies to polynomials. If we have a polynomial division problem, in this case, x to the 4th minus 13x squared plus 36 divided by x plus 2 is equal to x to the 3rd minus 2x to the 2nd minus 9x plus 18. Any polynomial division problem with a remainder of 0 can be rewritten as a multiplication problem by multiplying the quotient times the divisor, and it equals the dividend. So the quotient, x to the 3rd minus 2x squared minus 9x plus 18, times the divisor, x plus 2, is equal to the dividend, x to the 4th minus 13x squared plus 36. Go ahead, distribute it all out, combine like terms, some stuff will cancel, and if done correctly, you should wind up here. So how does that help us? Well, let's pretend we're back in the previous section and we're trying to solve, we need to set up a function. So let's suppose f of x equals x to the 4th minus 13x squared plus 36. In other words, the dividend in our division problem. And we were trying to find the x-intercepts by solving f of x is equal to 0. Well, if we start with x to the 4th minus 13x squared plus 36 equals 0, we might be stuck because it's not quadratic. It's quadratic-like. It's not quadratic, and so conventional factoring techniques wouldn't apply. However, thanks to this division problem, we have a factorization for that polynomial. We know that x to the 4th minus 13x squared plus 36 will factor into x cubed minus 2x squared minus 9x plus 18 and factor into x plus 2. Those are two of its factors. Hooray! If we're solving an equation equal to 0, factored is good. I can put x plus 2 equal to 0 and solve that easily. One of my x-intercepts is at -2 because one of the zeros of the function is -2. Now, what about this guy? Well, we'll talk about him in a minute. But at least we got it partially factored, and we got one of its solutions. Now, those of you who are on top of your factoring game might recognize that you can factor this by grouping. That won't always be the case, and we won't treat it as such, but we could continue. So what can we glean from what just happened here? Well, if you're looking for a solution of an equation, or more specifically, if you're looking for a 0 of a polynomial function, remember, a 0 is a value that makes the function equal to 0. Now we could check that by plugging in -2, and we would end up getting 0. Check it out if you don't believe me. But this 0 came from a factor, and this factor gave us a 0. There's a theorem called the factor theorem. A theorem is just a mathematical statement that has been proven true, so we know that it's always true. As opposed to a conjecture, which is something that we think is true, but either we can't prove it or it's impossible to prove. There are such things as conjectures that cannot be proven, a little bit beyond what we can talk about right now. But the factor theorem goes something like this. X equals a number, we'll say x equals c, is a zero of a function, f of x, if and only if f of x divided by x minus c has a remainder of 0. And we can actually stick a third thing into this equivalency. So I'm going to write if and only if again. This is not really part of the factor theorem, but it sort of is. It has something to do with something called the remainder theorem, which we're going to skip for the sake of time. But think about it. If this is a zero, well, it's just the definition of a zero function, so I don't really need this. If you're a zero of a function, in other words, that means f of c is equal to 0. So if a number goes into the function and comes out 0, that means that there's a factor associated with it, x minus that number. So I guess the bigger thing is, this is a 0, this is a factor. And the reason the signs are opposite is when you solve this equation, you have to do the opposite and move on both sides, and therefore it changes signs. That's a pretty powerful tool. It says if we know a number that makes u equal to 0, we can reverse engineer it back into a factor. By definition, a factor has a remainder of 0 when we divide, which means we can set up a division problem to find another factor. So that's pretty handy. And I'm going to show you how to capitalize it on it in the next video.